Welcome to Lesson 1 of Applied Physics. In this lesson, you will cover the following objectives. Discuss what physics is and describe some of the areas that fall into the science called physics. State the difference between a unit and a dimension. Convert between systems of units. And solve problems using a structured approach. This is a wordle of the many topics that you will see during this course on applied physics. You should first understand the physics terms and scientific units involved before you dive too deeply into the course. These are the base quantities, their units, and the associated symbol. Are you familiar with any of these quantities already? This lesson helps to explain the mathematical tools used for physics. You will have a difficult time doing physics if you can't do some algebra and trigonometry. Hopefully the first couple of lessons will assist you in either learning or refreshing your skills in this area. Physics is the fundamental science and the foundation of other physical sciences. Physics is divided into 5 major areas: mechanics, thermodynamics, electromagnetism, relativity, and quantum mechanics. Click on each image to learn more. According to Funk and Wagnalls, physics is a science dealing with the fundamental parts of the universe, the forces they exert on one another, and the results produced by these forces. More simply, physics is the study of the world in which we live. We will review the basic topics to study in this semester. These topics fall into the following classes: classical physics, physics of everyday life, relativistic physics, physics of very high speeds, and quantum physics, the physics of very small sizes. So, what is this physics? The realm of each of these areas of physics is shown here. Notice classic physics is what we see every day. It's large objects going at relatively slow speeds. But notice that the smaller we get, the closer we get toward the quantum physics side. The faster we travel, the more we head toward relativistic quantum physics. So we have classic physics, slow and large, quantum physics, the very small, and relativistic quantum physics, the very small and very fast. Mechanics, also known as classical physics, has many basic principles that are used in the other major areas. It is based on studies of motion by the Greeks through Galileo. Newton's Principia in 1687 is the basis of our study of mechanics. Measurements form the basis of testing theories in science, and we need to have consistent systems of units for the measurements. Uncertainties are inherent in all measurements, so we need rules for dealing with the uncertainties. A calculator, vernier caliper, and micrometer are oftentimes useful measuring tools in the physics classroom. We start our background discussion by reviewing what is meant by the dimension of a quantity. A dimension is a physical parameter regarded as a fundamental type of measure. Examples of dimensions are length, mass, and time. Whenever we refer to a dimension, we will use a capital letter inside square brackets. As an example, we will use L to denote the dimension of length. Here is something extra to think about. Physics is oftentimes presented in modern movies. Is it good physics or incorrect physics? Here's an example which you might want to ponder on. When talking of systems of measurement, one should always look for standardized systems. This is agreed upon by some authority, usually a governmental body. The Système International de Units, the International System of Units, was agreed to in 1960 by an international committee. It is the main system used in this text. It is also called MKS for the first letters in the units of the fundamental quantities of the SI system. Chemistry researchers and the medical profession tend to use the Gaussian system. In the United States, we are partial to the use of the U.S. customary system, even though, historically speaking, in the 1960s, U.S. research scientists were presented with the following poster to help understand the conversion to the metric system. America hasn't followed the rest of the world in a change to the metric system. Note, some people have said that the cartoon is not politically correct in these touchy times. How short are the memories of the British? In 1969, the British government established a metrication board to promote wider use of the metric system. As part of this effort, the United Kingdom Metric Association and the Construction Industry Training Board distributed a series of posters to promote wider understanding of the metric system. One of these is reproduced here as a public service, to remind people of simpler times when even government agencies were not shy about promoting a good cause using attention-getting methods. It depicts a bikini-clad gal with her measurements boldly indicated in centimeters on the left and in inches on the right in subdued gray. She quickly gained the affectionate name Miss Metric. This is strictly a historical reference and has been added to remind you that inappropriate treatment of employees could lead to undesired consequences. The three fundamental quantities needed for a measurement system are length, mass, and time. These are called fundamental because they are defined as the simple, most basic measurable quantities which must be used to create a measurement system. Read this quote from Lord Kelvin. "When you can measure what you are speaking about and express it in numbers, you know something about it. When you cannot express it in numbers, your knowledge is of a meager and unsatisfactory kind. It may be the beginning of knowledge, but you have scarcely, in your thoughts, advanced to the stage of science." For engineers, adaptations of the words and units is essential for building and understanding the nature of science. A closely related concept is that of a unit. A unit is different from a dimension in that a unit is very specific. A dimension is a general category. Examples of units corresponding to the dimension of length are inches, feet, miles, centimeters, kilometers, light years, and parsecs. Here are some examples of English units: the yard, the inch, the gallon, and the pound. Many times we need to work with conversions from English units to the metric system units. Here is an example of the types of length unit conversions that could take place. You can also go to this website and download an application for your portable mobile device and have a handy unit converter available at the touch of your fingers on your phone. These conversion factors and this application could be quite useful in any future job as a technician. Dimensional and unit analysis is one of the most essential learning tools you will receive in this course. In order for an equation to be valid, each term in the equation must have the same dimension. This is a necessary but not a sufficient condition for validity. That is, each term in an equation can have the same dimension and yet that equation not be valid. In order to add or subtract terms in an equation, both terms must be expressed in the same units. This is the single most significant idea that is used to get your units in physics equations proper. Physics problems must be done in appropriate units. Please carefully study and understand the next series of pages. Here is an example. Suppose that in these expressions shown, x has the dimension of length, t has the dimension of time, v has the dimension of length per time or length divided by time, and a has the dimension of length divided by time squared. Is each expression a valid equation? Take a moment to check for yourself. Information on the following page will help you determine if it is dimensionally valid and will show you how to verify this concept. Here's the solution to our example. To use dimensional analysis to test the validity, substitute the dimensions for each quantity. Notice for the left side, v squared equals a times x. A velocity is a length divided by time. An acceleration is a length divided by time squared. And x is a position or the dimension length. If you do the appropriate calculations and unit conversions, you can see that the expression may be valid. For the right side, x equals v times t plus a divided by t. Is this equation valid? The x position has the dimension of length, velocity is length divided by time, and time in seconds is a dimension of t. Including the dimensions for acceleration and then doing the simplification, we can see that the expression is false. SI units and dimensional analysis are processes you must learn. How can you use dimensional analysis to convert from inches to feet? Review this diagram. With a starting amount of 24 inches, equal amounts 1 foot, 12 inches. How many feet do you have? Notice 24 inches multiplied by the magic 1 expression of 1 foot equals 12 inches. The inches cancel, equaling 2 feet. How can you use dimensional analysis to calculate how many people make up 58 hands? Again, start with 58 hands. You know that on every hand there are 5 fingers. Putting fingers on top of the expression and hand on the bottom, you can cancel the term hand. Every single person has 10 fingers, so placing one person above 10 fingers, you can now cross out the number of fingers. Finally, multiply everything on top and divide by everything on the bottom, you come up with 29 people. Dimensional analysis is a win tax good friend. With European wind companies using the metric system, there is no telling how many times you might need to use dimensional analysis to make sure you're talking the same language of measurement. The algebraic manipulation performed on a physical quantity must be performed on both its magnitude and its units. To understand the value of the result of the algebraic manipulation, the units of measure used must be consistent. Often, though, the units of measure used in the experiment are convenient to the experiment but not consistent with the problem to be solved. Thus, we need to recognize what the unit of measure should be for an answer, and we need to express the measures in a consistent system of measures, usually the SI units. Re-examine these two examples and then do the self-check on the following page to see if you need to refresh your knowledge of the use of units of measure in dimensional analysis. A base unit is a defined amount. For example, someone decided that a particular distance was a good increment to measure with and defined that distance to be a meter. There is no other way to come up with a meter other than to go by the definition. A derived unit is some combination of base units. Speed has a derived unit of meter per second made up of the base units meter and second. It takes 7 base units to uniquely define a unit system. Do you know what each of these 7 symbols represent?